Welcome to Decoding Complexities. I'm Pradeep. Imagine you have a dataset with hundreds of features, each represented by a vector. Together, these vectors can describe a vast world of possibilities. But is this the most efficient way to do it? Do we really need all of these vectors to define our world? This leads to a fundamental engineering question. What is the smallest possible set of building blocks we need to describe our entire data space? The answer lies in the concept of span, basis, and dimension. And understanding them is the key to working with high dimensional data efficiently. Let's start with our collection of vectors. Any set of vectors that can be combined to reach every point in a space is called a generating set for that space. The set of all possible points we can reach by adding and scaling these vectors in your generating set is called the span. But look closely. We know from our last video that these three vectors are linearly dependent. v3 is just v1 plus v2. It's a redundant building block. We can still reach every point in the plane using only v1 and v2. Our generating set is inefficient. It works, but it's bloated. So, this leads to the question, what is the best generating set? This brings us to the star of the show, the basis. A basis for a vector space is a set of vectors that satisfies two strict conditions. One, the set must be linearly independent. And second, the set must span the entire space. A basis is the ultimate Lego starter kit. It contains the absolute minimum number of unique, non-redundant pieces you need to build every single thing possible in your world. The standard basis is the most famous example. These two vectors are obviously linearly independent, and we know they span the 2D plane. But is a basis unique? Absolutely not. Any set of two linearly independent vectors is a valid basis for the 2D plane. They just provide a different coordinate system, a different point of view on the same world. Once we understand the basis, the concept of dimension becomes incredibly simple. The dimension of a vector space is just the number of vectors in its basis. If a space has a basis with two vectors, its dimension is 2. If it has a basis with 3 vectors, its dimension is 3. It's that straightforward. But what happens when we apply a matrix transformation? This is where we need the concept of rank. The rank of a matrix is the dimension of its output space. In this case, our matrix took a 2-dimensional input and squashed it into a 1-dimensional output. Therefore, the rank of this matrix is 1. It lost information. The rank tells you the true dimensionality of the information coming out of a matrix operation. A full rank matrix preserves the dimension. A rank deficient matrix loses dimension, meaning some of the original information is squashed. So, how do we calculate these? The most reliable way to find the rank of a matrix is to use the technique from our last video, Gaussian elimination. The rank of a matrix is simply the number of pivots or non-zero rows in its row echelon form. In this case, we have 2 pivots, so the rank is 2. This means our 3D data is being squashed into a 2D plane. In Python, this is trivial with NumPy. The matrix rank function handles all the complex computation for us and directly gives us the dimension of the output space. So, we started with a messy generating set. We found the efficient non-redundant basis within it. The number of vectors in that basis gave us the dimension of our space. And finally, the dimension of a matrix output gave us its rank. These concepts are foundation for understanding the true shape and complexity of our data. But what if our building blocks, our basis vectors, weren't just independent, but were also perfectly perpendicular to each other? What if they were all exactly 1 unit long? This leads to the gold standard of coordinate systems, a set of building blocks that makes all the math and all the computation dramatically simpler and more stable. If this deep dive was helpful, hitting the like button tells me to make more videos just like this. Be sure to subscribe because in our next video, we will decode orthogonality and the gold standard of building blocks, the orthonormal basis. Thank you for watching, and I will see you in the next one.